approach at the moment. So that was first way of doing analysis. And what is the Lagrangian approach? Anyone?
Start over and give it average of a single of a single point or maybe individually
Oh, yeah.
different groups.
Basically, we follow an individual particle along its path, and we record the properties as it moves along its path. So that is the Lagrangian approach, and it is analogous to we call it system approach. In thermodynamics, you must have learned about system, and then the second one is Eulerian approach. So in Eulerian approach, we fix a point in space, and then we analyze the particles which move through that fixed point. So if I give you a practical example, that if you want to differentiate between these two approaches, if you ever ride a bike or a car, you can see a speedometer in front of it. So it gives us the real time value for the velocity or speed of the vehicle. So that is basically Lagrangian approach. But if you travel on a road and then there is some traffic police sitting with a speed gun, so that is they are going to record your speed when you approach them. So that is the Eulerian approach. Right, so the Lagrangian approach is the speedometer of your vehicle, and for the Eulerian approach, that is the speed current which is being used by traffic police to record the speed of your vehicle. Right, so that is kind of a difference between Lagrangian and Eulerian approach. Right, so I hope that, and we also call it control volume approach. Right. And after that, if we want to switch from Lagrangian to Eulerian approach, how do we do that? Is there a way?
Sir, we use
Yes, sir.
Reynolds.
Lagrangian फार्मूला होता है और यूलियन हमारे पास पॉइंट्स होते हैं, उस पॉइंट्स को
जी,
इक्वेशन में पुट
लेकिन
करेंगे तो हमारे पास यूलियन फार्मूला आ जाएगा।
वो कौन सी इक्वेशन होती है जी?
यस सर, रेनॉल्ड ट्रांसफर थ्योरम यूज करते हैं।
बिल्कुल जी, उसको हम कहते हैं, थैंक यू वेरी मच, दैट इज रेनॉल्ड्स ट्रांसपोर्ट थ्योरम। Okay, first of all, why we need to convert from Lagrangian to Eulerian approach? First of all, why there is a need to change from Lagrangian to Eulerian approach?
Yes, sir, because the observation of Lagrangian approach is much more difficult.
Why?
Because we have to बेसिकली सर उसमें हमने ये करना होता है कि हर पार्टिकल को अप्रोच करके हर पार्टिकल की अलग अलग प्रॉपर्टीज को उसमें करना होता है। उसमें हम यूलेरियन में ये करते हैं कि हम एक फिक्स वॉल्यूम कर लेते हैं और वहां से जो भी पार्टिकल गुजर रहा है उसकी हम मतलब जो प्रॉपर्टीज हैं उसको हम मेजर कर लेते हैं, तो वो एक मतलब इजी वे है हमारे लिए। इसलिए हम चाहते हैं कि जो लैग्रांजियन है पूरा उसको यूलेरियन में हम कर चेंज कर दें।
थैंक यू वेरी मच हसन। आई थिंक योर नेम इज हसन।
हसन मुस्तफा सर।
Okay, Hassan Mustafa, thank you very much for the clarification. It couldn't be any better. So you are absolutely right, because in the Lagrangian approach, because we are following the system, and in system we have got infinite particles. So it is basically impractical to follow each particle. So rather to do this, we kind of define our space in a fixed volume in space, so that we can observe the particles which passes through those fixed space. So that is the Eulerian approach. So that's why we need Reynolds transport theorem to analyze in control volume space, because we know that all the physical laws, they are applicable for the system approach, not for the control volume approach. So that's why we need that convergence from system to control volume approach. So if we write the Reynolds transport theorem for an extensive property B, so we can write it dV by dt, that is equal to partial by partial t rho into B into rho B into dV. This is control volume. We have to integrate it, and then we need the inflow and outflow term, which is across the control surface, and that is rho B into V dot N dA. Here B is the extensive property which depends upon the mass of the system, and B is the intensive property which is independent of mass of the system, right? So this is the system approach, the left hand side, and the right hand side is the control volume approach. So we talk about the change in time rate change of that property within that control volume, and whatever inflow and outflow of that property from that control volume. So we are going to use this for our analysis in FM2, fluid mechanics 2. So now let us start discussing the. Let me open the lecture slide. So you know my name. That is. So we are going to continue with the same book. So we have got 3 credit hours like course. So it means that I think the course code is ME230, and we have got credit hours which is 3. So it means that we have got 2 credit hour class on Tuesday and 1 credit hour class on Friday, and then there are contact hours. So that is also 3. So they are basically the same number of hours which I am supposed to be in contact with you. So, but it depends upon you that if you have got any query, we can always discuss your queries in online MST meeting, one-to-one meeting, or you can, if you want, and the situation gets better, then you can also discuss it in face-to-face mode in the university as well, in my office, which is the differential analysis of the fluid flow. So up till now we have covered implicit flows in which there was no friction involved. So now we are going to include that contribution of friction within the flow, because we know that the viscosity of a fluid, that is the resistance to flow. So in that differential analysis, we can do very detailed analysis of a flow field, because in the finite control volume approach we can only concerned about the inflow and outflow at the boundary, but in differential analysis we are going to discuss the detailed flow field. So in that the viscosity would come into effect, and then we are going to discuss about the dynamics of the fluid. So in this chapter we are going to discuss the forces as well which are producing the fluid flow and which are affecting the fluid flow. So and then we are going to derive the governing equation for the viscous flow, which are Navier-Stokes equations, right? So that is for the that are the equations which governs the actual flow field, and then that would be covered in chapter number 6, which is the differential analysis for the fluid flow. After that, we are going to discuss the viscous flow pipe. So if you observe that in nature there are 2 types of flow. One is internal flows, in which they are bounded flows, like any example of internal flow, like flow through pipes, flow through blood veins, flow through your arteries, and flow through your lungs. So all are the examples of internal flows, which are bounded flows. So it means that we have got the something like duct flow, pipe flow, anything which is bounded, right? And then that is the example of internal flow. So in chapter number 8, we are going to discuss the all the features of internal flow. So we know that if the flow is bounded, there would be some kind of let me when we have got internal flows, like if we have got a pipe flow. So in pipe flow, what happens that if the flow is happening, so there would be a drag force which would be applied, or the resistance force which would be applied by this surface on the moving fluid. So that is called the drag force or shear force. So that is we have to take into account, because that force would drop the pressure along the flow. It means that pressure at this end would be higher, and pressure at the grid of the pipe would be lower. And if you realize that we usually put a pump here. If we want to drive some flow through pipe, then we use pump or we use elevation. For the elevation, we don't need pump. Like in your homes, there would be some overhead tank. So from there, if you want to have the flow of water, you just switch on the open the tap in your sink, and then water comes due to that elevation difference. But if you want to flow that make that flow happen from the underground tank to overhead tank, then you need some kind of pump to drive that flow against the elevation. So we use pump for usually for the flow of liquid, and compressor for the for building the pressure in a gas. So because we are talking about fluid mechanics, so we are going to discuss hydraulics, which are liquids, uh, in more detail. Right. So in this we have got major losses and minor losses. Major losses I have told you that are due to friction, frictional losses, which are present at the pipe surface, and then minor losses. Minor losses are due to some valve bend, anything which is we have got sudden expansion, sudden T we joint, and those are due to those sudden changes. Those losses are minor losses. So that is chapter number 8, in which we are going to cover major losses and minor losses in internal flow. And then chapter number we have got chapter number 9, which are flow over immersed bodies. So now this was which I have covered here. That is internal flow, and then we have got second type of flows. They are external flows. Any example of external flows? Practical example you can think of.
Sir,
Flow through
canals.
rivers.
Submarines.
Flow over submarines, flow over any vehicle, whether that is ground vehicle or aero vehicle, like aeroplane or above, your car, bus, those are, or flow over buildings, flow
So
over
airflow
vehicles,
around buildings.
airflow over buildings, all are those flows. They are called external flows. So it means that there is no boundary for there is fluid solid interaction, but there is no bounding of that flow, because on the other side you have got open space to flow. So those are called external flow. So flow over vehicles, flow over buildings, flow over missiles, flow over spaceships. So all these flows are external flows. So in external flows, we have got two major forces. One is drag force, and the other one is lift force. So drag force is usually in the direction parallel to the flow, but in the opposite direction. But lift force is usually in the direction perpendicular to the flow, which means that that lift force was responsible for the aeroplanes to fly. So we are going to discuss these two forces in and how they are being changed or how they are being calculated for different kind of geometries in chapter number 9, which is flow over immersed bodies. Okay, so and that is which we are going to cover in chapter number 9. And then we are going to, because compressible flows are the flows through the nozzle, and open channel flows that are the flow through canals. So we are not going to discuss these things in detail, because compressible flows, they are being discussed in thermodynamics, in which you must have you taken a course of thermodynamics too after now, or you are taking a course now?
Yes, sir, in this semester.
Okay, so you are going to discuss. Discuss compressible flows, in which the flow through nozzles and diffusers and things like that. In that, so we are not going to discuss that. But instead, we are going to move on to the most interesting topic for the fluid mechanics, which is turbo machines. Because turbo machines is the major application area of fluid mechanics. So any turbo machine you can think of, anything turbo machine related, which you can think of.
Sir, water pumps.
Water pumps, excellent. Anything else?
Compressor.
Compressor,
Dams.
compressor, compressor, pump, turbine,
डैम्स आएंगे सर
बिल्कुल हाइड्रोलिक डैम्स वो उसमें आ जाते हैं, विंड टरबाइन भी आ जाता है, हाइड्रोलिक टरबाइन भी आ जाते हैं जो कि डैम्स होते हैं बिल्कुल। तो यहाँ पे देखा जाए तो अगर फ्लूइड मैकेनिक्स की जो डायरेक्ट एप्लीकेशन है वो टर्बो मशीनरी में है। Turbo machinery involves some kind of rotation of some rotor blade. So either we provide electric work, when we provide electric work, that is kind of pump or compressor, in which we are being driving that turbo machine by the provision of electricity. So we are inputting the work into that turbo machine so that we can either raise the pressure of the fluid or we can compress it like in compressor, or we can raise the pressure of the fluid so that it can flow. And the second type of turbo machines are turbines or dams. So they are basically the work producing turbo machines. So we extract the work from them by the flow of fluid over it, like wind turbines, or on wind turbines what happens that the air comes and strikes with the blade, and that makes the blades to rotate, and then we have placed a generator connected with the shaft of that wind turbine, and then we can produce electricity from there. That or steam turbine or gas turbine, so they also work on the same principle, that they are being moved by the flow of fluid on that. So turbo machines, they are the basic what do you call that application of fluid mechanics. So we would try to cover as much as possible from the turbo machines, so that you can be well equipped with the fundamental principle of these two types of turbo machines. And so these are the four major topics which we are going to cover in this here. So one is the differential analysis of the fluid flow, which is chapter number 6. As I have discussed, that we are going to discuss here. We are going to derive the linear of equation, which are derived by the conservation of mass and momentum for the fluid element or fluid particle, and then we would discuss some of the simplified solution for the viscous incompressible flow. So the major limitation of Bernoulli equation is that it only applicable for the inviscid fluid where there is no viscosity, and then secondly it is only applicable for the steady flow which is not changing in time. So for the moment, okay, just a minute. So I was discussing about the course content. So in chapter number 6, we are going to discuss the viscous flows and the equations which govern the viscous flows, which are Navier-Stokes equations. So we are going to discuss its derivation by the conservation of mass and momentum for the fluid element, and then we would discuss the solution for the Navier-Stokes equation for some simplified cases like laminar flow through a pipe and laminar flow through a duct. So those are the simplified solutions we can have, but usually we cannot solve those equations by analytic method. So we need to do some kind of numerical analysis. So have you heard a name of software which is software? Anyone?
Yes, sir.
yes
So
sir
ANSYS software do the numerical solution.
Yes, sir.
Thank you very much for your input. Numerical solution of Navier-Stokes equation, and it also being used for the stress analysis purpose. So and for the fluid flow, it solves the numerical solution. So numerical solution means that we don't solve the exact equation, but we kind of discretize a domain into small segments. And like if we have got this domain, so we kind of uh, divide it into small segments by generating the grid like this, and then we write the governing equation, which are Navier-Stokes equation, on these intersecting points, and then we solve it numerically. Right, on these discrete points, we try to find the velocity and pressure, density, temperature, So that is called the numerical solution. So that is not the continuous solution, but that is the discrete solution of the Navier-Stokes equation. So for that we use ANSYS. So why we need ANSYS? Because we cannot solve the Navier-Stokes equation mathematically or analytically. So that's why we require the numerical solution by the ANSYS. So I would also guide you about that how to do this analysis by using the software of ANSYS. So I would provide you some initial guidance about this and give you a project on this software ANSYS, and would provide you with the tutorials and everything set up so that you can get familiarized with this numerical solver, which is ANSYS. So that would be a good learning curve for you guys. Okay, so that was chapter number 6. After that, we are going to discuss the viscous flow through pipes. So as I have told you that we are going to discuss major and minor losses for the laminar and turbulent flows. So major losses are due to friction and minor losses are due to different components which are installed during that piping, like valves, teeth, or any sudden expansion, sudden contraction, anything like that. So those are comes into minor losses, which are due to those components installed in that piping system. And then this is chapter number 6, the viscous flow in pipes, that is chapter number 8. Then chapter number 9 is the flow over immersed bodies. So that is flow, external flow. We are going to discuss lift and drag concept for different kinds of symmetry, boundary layer and boundary layer solutions in this chapter. So that is chapter number 9. And then because for the turbo machines we need angular momentum equation solution, so we are going to discuss this thing in movement of momentum equation, which is chapter number 12, and turbo machines as well, which is centrifugal and axial pumps, then turbines, which are impulse and reaction turbines. So in chapter number 12 we are going to discuss that can we how can we select a pump for a particular application, and then what are the pump performance curves, and then we are going to discuss about impulse and reaction turbines, which are used for the in hydraulic dams. Okay, and what is their working principle. So these are the course contents for this course. So any query in this? Okay, so because it is very important to know that this is an application course, because in the fluid mechanics one you have learned about basic fundamentals. So now we are going to use those fundamentals to build some to apply those concepts on some application areas. Okay, so all these viscous flow through pipes and flow over immersed bodies and turbo machines, they are application areas of fluid mechanics. So and now, okay, before we start, just what is continuum hypothesis? Anyone?
एवरेज एनालिसिस होता है इस चीज का, यानी कि हम एक पार्टिकल को नहीं देख रहे, मतलब हम एवरेज जगह की बात करेंगे, एक सर्टेन एरिया में क्या हमारे पास कंडीशंस वगैरह, तो
बिल्कुल जी. Thank you very much. You are correct that in continuum analysis we say that we are not considering the properties of individual molecules. Rather than we take average properties of a bundle of particles, so that whenever we kind of if we are kind of plotting some property like pressure, velocity, or temperature, so that would be a continuous function. So if we talk about molecular level, then it would be very chaotic like this. But because we are talking about the average properties, so it means that the property changes in space or time would be continuous function. It means that is kind of very smooth function. So that is the purpose of continuum hypothesis, that we are considering about the average properties. We are not considering the properties of individual molecules, right? And then now we quickly, if I can tell you about basic recap that which we have covered up to now. So first of all, differential analysis, why we need it? Because you have already discussed the finite controlled volume approach, which was chapter number 5. So that is the approach which only requires the physical condition at the boundary. So we are not concerned about the detailed flow field. So it means that it is unable to provide detailed flow field information. That it means that it can only provide you some integral properties, but it cannot give you the detailed flow field at inside the that area of interest. So or the volume of interest. So differential analysis, that is usually it is used to obtain the detailed knowledge of flow field. So how do we determine the detailed knowledge of the flow field? By solving the Navier-Stokes equation at inside the flow field. And then this differential analysis is being done on infinite decimal node volume, and then we extend it to the whole flow field, right? So how it is being done, we are going to study in detail in the coming lecture. And then the governing equations obtained by differential analysis are rather complicated, which are, as I have already told you, that those equations are Navier-Stokes equations, and there is no exact जनरल सोल्यूशन ऑफ द नेवियर स्टोक्स इक्वेशन। ठीक है, जनरल सोल्यूशन मतलब ये होता है कि जो हमारे पास 3 डायमेंशनल unsteady partial differential equation है, they wouldn't have any general solution. So it means that we need to do some kind of either simplifying assumptions for some simplified flows, like flow through laminar flows through pipes. We can get the exact solution, but it is only applicable to laminar flow through pipe, not for the turbulent flow over some vehicle. So we cannot apply over that. So it means that then we need to do the numerical solution. Okay, and to do the numerical solution, we use some kind of software. As I have already told you, that ANSYS is a software which is used for the CFD purpose. We call it computational fluid dynamics, or CFD, so that we can do the numerical solution. So maybe if you pursue your master's, or maybe it can be also offered to you in your final year as an elective course, computational fluid dynamics, in which you would study the numerical solution techniques for actual fluid flow analysis. So in this course, we are only limited to some analytic solutions, which are simplified solutions, right? But for the general solution, we need to do computational fluid dynamics, which is CFD. So maybe if you would be interested in that, it can be offered during your final year. Okay, but you would be, nevertheless, you would be doing one project for this group project on by using ANSYS software. So it would give you very good working that how to use that software to do the analysis. Okay, so hopefully we would learn quite a lot during that. So, okay, so now just a quick recap, continuing my hypothesis as we discussed, that we discussed about the average properties, velocity, that is basically a function of time as well as space in 3 dimensions. And if we want to know the okay, what is this approach? I have written like this equation. Is it Eurasian approach or Lagrangian approach? Anyone?
I think Lagrangian approach.
This is the Eulerian approach, because in the
Eulerian approach, sir.
Eulerian approach, we also need to know the coordinates on which there is a information of that property. For the Lagrangian approach, that is only function of time, because it means that we are moving with that particle. So we don't need to know the location of that particle, but only we need to know about at which time instant we are recording that property. Okay, and velocity magnitude, we know that we take the square, add them, and then take the under root. So that is the velocity magnitude, very simple thing. So all these things I just put, because they are from FM1. So then Eulerian approach, we know that for the Lagrangian approach, the properties are only function of time. For the Eulerian approach, that is also function of space. So fluid particles, when it travels in space, the acceleration, it is due to 2 factors. One is the time rate of change, and one is the spatial variation. If the unsteadiness, that is at one point, if the particles are moving through that point, how the velocity and other properties are changing at that particular point. So that is the unsteadiness. And the second spatial variation means that once a particle A, it moves from one location to another location, how its velocity varies. If its velocity changes, then it means that there would be acceleration. So that acceleration would be due to spatial variation. And if the acceleration is due to change in time, that is due to unsteadiness, right? So fluid particle acceleration, that is due to two things. One is time rate of change, and then the second thing is the spatial variation. So I hope that these concepts are clear from FM1. And how to write the acceleration, that is the time rate of dependence, that is the first term, partial v by partial t, and then the spatial variation, that is that how the velocity changes in space in x, y, and z direction. So if we write the acceleration, so that is the first term is the unsteadiness, that is the time rate of change at one point, and these other three terms, they are spatial variation of velocity. So they are due to variation in space for a particular fluid particle A. Okay, so we can write it in terms of this acceleration, and that is the same thing as we defined it for the material derivative. Material derivative, that is the sum of point variation plus space variation. So we can write the acceleration components in x, y, and z by using these relations. So I hope that you have learned these in chapter number 3, which was basically kinematics. I think it was chapter number 4. I think kinematics of fluid mechanics. So material derivative or substantial derivative. So I hope that these concepts are clear to everyone. If that's the case, okay, so we
6 मिनट की ब्रेक
continue, or we are going to start FM2 course from here. So a quick recap of FM1. So now we are going to discuss the deformation of a fluid element. That is the first topic of FM2. Deformation of fluid element or fluid particle. We cannot call it fluid element. So can you guess that how many, what types of if we take this one element, square element, so it can, after undergoing some distance, after traveling some distance, due to the influence of forces on it, which are we would talk about those forces in a minute. But deformation, what kind of deformation it can have? Maybe it would have something like, if I know, maybe it would have something like this shape, or so it means that if you see after time delta t, after traveling some distance here, so it would have some kind of change in its shape and volume as well as orientation. So because it looks very difficult to see it as it is, because we don't know that what are the changes. So if we want to write that how many changes are there, first of all, if you see that it was the point, it traveled, if we say that this was the origin of that element, so it traveled a distance. So that motion, that is called, we call it, motion of that, linear motion of that, we call it translation.
डिस्प्लेसमेंट क्या है सर?
डिस्प्लेसमेंट कह लें या ट्रांसलेशन कह लें, दैट इज बोथ आर इक्वली ट्रू, कोई फर्क नहीं दोनों में। ट्रांसलेशन का मतलब ये होता है ना कि वो डिस्प्लेस हो गया है फ्रॉम वन पॉइंट टू अनदर, दैट इज द सेम थिंग, बट इन डिफॉर्मेशन टर्म्स वी कॉल इट ट्रांसलेशन. But physically it means that it has been translated or displaced from one point to other. Okay, what other thing we can see here, that is linear deformation. Linear deformation. Linear deformation means that its volume has been volume changed. Then the third thing is the rotation. If you see here, it was parallel to x-axis, but here you can see that it has been rotated to some point. And then the fourth bit is that is angular deformation. Here volume change is there, but no shape change. Angular deformation, that is that from the original square shape, it has become some other shape. So maybe some other shape, maybe some distorted element. So that is we shape change. So these are the four deformations which fluid element experiences when it flows through a flow under the influence of forces. Now, talking about the forces, what kind of forces?
Translation or
yes.
translation or linear deformation और difference क्या होगा basically फिर?
Translation में okay, let me tell you. Translation is the we call it rigid body motion. ठीक है, यानी कि उसमें यह है कि वो पूरे का पूरा एलिमेंट एज अ रिजिड बॉडी इट हैज बीन डिस्प्लेस्ड फ्रॉम वन पॉइंट टू अनदर पॉइंट, और रोटेशन भी जो सी है ये भी एक तरह से काइंड ऑफ रिजिड बॉडी मोशन है. उसमें क्या होता है कि रिजिड बॉडी मोशन का मतलब ये है कि वो अपने एक्सिस के अबाउट रोटेट कर दिया है एज अ रिजिड बॉडी. इसी तरह ट्रांसलेशन भी रिजिड बॉडी मोशन है. लेकिन लीनियर डिफॉर्मेशन क्या है? लेट मी शो यू the difference between these two on a lecture slide. Maybe it would be more easier for you to see. Who asked the question? Can you please state your name?
Sir, Muhammad Umair Khalid.
Okay, Muhammad Umair Khalid. If you see here, translation. Can you see the lecture slide here?
Yes, sir.
Here, if you see that the whole element that has been displaced by a distance. Okay, for the translation, or we call it the linear motion. Okay, but linear deformation, if you see that its volume has been changed. Okay, it has been deformed linearly. Okay, now the second point is that what is the difference between linear deformation and the angular deformation? In linear deformation, it has been kind of a square. But for the angular deformation, if you see that now the shape of that object has been also changed. Okay? मोहम्मद उमैर खालिद. और रोटेशन और ट्रांसलेशन अगर आप देखें ना तो ये दोनों जो टाइप्स ऑफ डिफॉर्मेशन है ये रिजिड बॉडी डिफॉर्मेशन है, यानी कि उसमें पूरे का पूरा जो बॉडी है दैट हैज बीन आइदर ट्रांसलेटेड और रोटेटेड, but the shape and the volume hasn't been changed for both types of for the translation as well as for the rotation. Okay, but linear deformation the volume has been changed, and in the angular deformation the shape of that element has been changed. Okay, so now we have discussed these four types of deformation. Now, what kind of forces are there which can create these kind of deformation? There are basically in nature or for the fluid mechanics, there are two types of forces. One is, if you remember that, normal force, and one is shear force.
Shear force.
Shear force. Right? Shear force and normal force, they are the forces which create these deformations. Now, if we have got an element, let me explain it further now. If we have got an element and on this axis and on this we have got equal force, it means that F1 is equal to F2, right? Then if F1 is equal to F2, it means that it would be translated in X direction without any deformation. But what happens if F2 is bigger than F1? Then it would be elongated, right? It means that now we would have linear deformation. Linear deformation. If F1 is equal to F2, then it means that we would have translation, right? Okay, so this is the difference between, and what is the shear force? It means that if there is on this end we have got a force, and then we have got a force which is more on the upper side. It means that it would try to rotate in this. If this F3 force is more than F4, if F3 force is more than F4 force, then it would try to rotate in this direction. Right? So that is the concept of shear force. But how do we decide that? How to see that which forces would be produced in a flow field? For that, we need to see the velocity at each face of the element. So let me tell you that another figure. Here, if we talk about two-dimensional object, we would have here u velocity and here we would have v velocity. If at all the vertices, at all the points inside this fluid component, we have the same velocity u, v, u, and this is v, u, v, u. So it means that if at all the points we have got the same u and v velocity, then it means that there would be some kind of translation or linear motion of this object. So there wouldn't be any deformation. But if I say that here the velocity is more at this point, if it is u1 and this is u2, and u2 is bigger than u1, it means that now this object would be elongated, and if u2 is less than u1, then it would be kind of compressed a little bit. But now we need to see that how we can quantify these deformations by using the velocity information. Okay, so for that, let me let's consider that we have got this element, its size is delta y and delta x. So now we are talking about linear deformation. So if the velocity at this point is given and we want to determine the velocity at this point, and we know that the velocity is different, how can we determine that? Anyone? If we are given a function value at one point and we want to know the function value in the neighborhood, anything we can use, any series we can use to determine the value at the neighboring point? No. G. Have you heard the name Fourier series? Fourier series, ये आपको नाम सुना हुआ है?
Yes, sir.
Yes, sir.
उसमें क्या होता है? fx plus dx is equal to fx plus partial f by partial x into dx plus partial square f by partial x square dx square divided by delta x divided by 2, which is delta x is the distance plus so on. ठीक है, ये हमारे पास सीरीज होती है. So if we take only the first two terms and ignore the higher order terms, then here the velocity can be written as, if we want to write the velocity here, that would be u plus partial u by partial x into delta x. Okay, that is the velocity of this point. Okay, and if we want to know that how much elongation has been done in time delta t, so how can we? Okay, one thing you see that the necessary condition for the linear deformation is partial u by partial x. That is the now there are two types of velocity gradients. One is the normal gradients, and one is tangential gradients. नॉर्मल ग्रेडियंट्स कौन कौन से होते हैं जी? पार्शियल u by partial x, पार्शियल v by partial y, यानी कि जिस डायरेक्शन में वेलोसिटी है उसी डायरेक्शन में अगर वो वेलोसिटी चेंज हो रही है, देन दैट इज नॉर्मल वेलोसिटी ग्रेडियंट, एंड पार्शियल w by partial z. And similarly we have got partial For the tangential gradient, we have got partial u by partial y, partial u by partial z, partial v by partial x, partial v by partial z, and we have got partial w by partial x and partial w by partial z. So if you see here that the necessary condition for the linear deformation to occur, that there should be some normal gradient either in the x direction, y direction, or z direction, then we would have the linear deformity. Okay, so how much it would be deformed? How can we see that? ये डिफॉर्मेशन कितनी हुई है एक्स में? अगर वो देखनी हो कि लीनियर डिफॉर्मेशन हुई कितनी है, तो चेंज इन वॉल्यूम अगर हमें निकालना हो तो वो कैसे निकाल सकते हैं हम? पार्शियल यू बाय पार्शियल एक्स इंटू डेल्टा एक्स. अच्छा, अब अगर हम इसको यहाँ, क्योंकि यू और यू तो कैंसिल हो जाएगा, चेंज इन, अगर आपने वेलोसिटी निकालनी है तो चेंज इन, ये जो वेलोसिटी है पार्शियल यू बाय पार्शियल एक्स इंटू डेल्टा एक्स है. तो अगर हमने ये देखना है कि हाउ मच वॉल्यूम हैज बीन चेंज फॉर दिस एलिमेंट, सो दैट वुड बी इक्वल टू partial u by partial x into delta x. Now change in volume. So first of all, if we kind of do some dimensional analysis here, delta x would be cancelled out with delta x. So what is the unit of u? Velocity unit क्या होता है जी?
मीटर्स पर सेकंड.
मीटर पर
मीटर पर
सेकंड.
सेकंड.
इसका मतलब ये है कि हमें डेल्टा टी से मल्टीप्लाई करना पड़ेगा टू मेक इट मीटर. ठीक है, यानी कि इन टाइम डेल्टा टी हाउ मच इट हैज बीन डिफॉर्म्ड, सो देयर डेल्टा टी हैज बीन मल्टीप्लाइड. नाउ दिस इज द डिफॉर्मेशन in length. If we want to see how much it has been deformed in terms of volume, so it means that we need to multiply it with the area, which is the, what is the surface area of this, if we see this surface area would be delta y into delta z. Okay, so we have got, if I write it here now, change in volume in x direction that would be equal to partial u by partial x into delta t into delta x, delta y, and delta z. What is this? This is the differential control, initial differential control volume of the element. So we have got change in volume in x direction. So have you understood this point? That how I have taken change in volume in the x direction. So I have taken the velocity gradient, multiplied it with the time interval in which the deformation has been occurred, and then multiplied it with the surface area where the that deformation is taking place. Okay. This delta x was here due to that Fourier series expansion which we have treated. So now if we write change in volume in x direction per unit volume. Okay. Now we need to write. Is there any query up till here? Any confusion you can ask anytime. I am happy to repeat.
सर पार्शियल यू बाय पार्शियल एक्स मल्टीप्लाई बाय डेल्टा एक्स. सर ये पॉइंट समझ नहीं कैसे हुआ. ये तो पता लग गया जिस तरह आपने पार्शियल यू बाय पार्शियल एक्स निकाला था कि हम एक्स निकाल रहे हैं.
ठीक है जी, मैं दोबारा रिपीट कर देता हूँ. नो वरीज. ये देखिए ना, फोरियर सीरीज है. प्लीज स्टेट योर नेम बेटा सो दैट आई कैन.
सर
जी
तलहा. सर तलहा नाम है
जी. एक्सीलेंट नेम. ओके जी. So Talha, we have got a u plus. If you see the Fourier series, that if we want to determine the function value in the neighborhood, we do this f of x plus partial f by partial x into dx. Do you understand this point?
यस सर, ये तो पता लग गया.
अगर यहाँ पे अगर u वेलोसिटी है और उसके नेबरिंग पॉइंट पे जो डेल्टा x के बाद हमने वेलोसिटी निकालनी है, तो अगर हम फोरियर सीरीज से निकालना चाहें तो वो क्या आ जाएगा? u प्लस पार्शियल u बाय पार्शियल x. यहाँ पे टैली कर ले, f की जगह अगर हम u पुट करें तो पार्शियल u बाय पार्शियल x इनटू डेल्टा x, ये वही चीज हो जाएगी.
सर इसमें जो नेबर वाला आप कह रहे हैं, जो नेबर में हम लोगों ने वेलोसिटी फाइंड करनी है, वो इसमें कौन सी चीज रिप्रेजेंट कर रही है? इसमें u प्लस
ये वाला पॉइंट है. सॉरी एक मिनट, मैं ए पॉइंट जो सा था वो ओरिजिनल पॉइंट था. इफ आई राइट इट हियर, ये ए पॉइंट है, ये बी पॉइंट है। ए पॉइंट पे हमें पता है कि वेलोसिटी है यू, हमने बी पॉइंट पे निकालनी है, ठीक है।
ठीक है सर।
तो बी पॉइंट पे निकालनी है, तो वो ए पॉइंट पे जो वेलोसिटी है वो यू, जो कि ये एफ ऑफ एक्स है प्लस पार्शियल यू बाई पार्शियल एक्स, एफ की जगह आप यू पुट कर दें, पार्शियल यू बाई पार्शियल एक्स इनटू डेल्टा एक्स, और ये डीएक्स लिखा हुआ है, ठीक है। और हायर ऑर्डर हमने उसको निगलेक्ट कर दिया, ठीक है।
ठीक है सर, ठीक है।
ओके जी, थैंक यू। तो आई होप दैट दिस पॉइंट इज क्लियर। अब हमने ये निकाल लिया ए और बी पॉइंट पे। अगर हमने निकालना है कि भाई इस वेलोसिटी चेंज की वजह से वॉल्यूम में क्या फर्क पड़ा है, तो वो चेंज इन वेलोसिटी आएगी। चेंज इन वेलोसिटी क्या होगी, वेलोसिटी एट बी माइनस वेलोसिटी एट ए। तो उसमें क्या हो जाएगा कि ये यू और ये यू कैंसिल आउट हो जाएंगे, बाकी जो बचेगा पार्शियल यू बाई पार्शियल एक्स इनटू डेल्टा एक्स। और वहां से अगर हमें चेंज इन वॉल्यूम निकालना है तो फिर हमें डेल्टा टी और डेल्टा वाई और डेल्टा जी से मल्टीप्लाई करना पड़ेगा। तो वो जब हम करते हैं तो हमारे पास चेंज इन वॉल्यूम इन एक्स डायरेक्शन आ गया। अब अगर हमने चेंज इन वॉल्यूम in x direction पर यूनिट वॉल्यूम निकालना हो, पर यूनिट वॉल्यूम क्या है कि इस पूरी चीज को आप 1 डेल्टा एक्स डेल वाई और डेल जी से यहाँ पे ये पूरी चीज आ जाए। तो अगर आप देखें तो यहाँ पे ये वाली चीज है और ये वाली चीज है, ये कैंसिल आउट हो जाएगा, ठीक है जी। एनी प्रॉब्लम इन दिस?
यस सर, ठीक है।
ठीक है। तो हमारे पास बाकी जो बचेगा वो अगर मैं यहाँ पे लिख दूं, that would be equal to partial u by partial x into delta t. Now, if we want to know the rate of change of volume per unit, यानी कि यहाँ पे मैं कहता हूँ कि मैंने यहाँ पे कैलकुलेट करना है,
सर डिवाइडेड बाय टाइम हो जाएगा,
डिवाइडेड बाय टाइम हो जाएगा, रेट ऑफ चेंज ऑफ दिस टोटल। तो वो हमारे पास हो जाएगा लिमिट डेल्टा टी इक्वल टू 0 एंड दिस बिट डिवाइडेड बाय डेल्टा टी। तो वो कैंसिल आउट हो जाएगा और आपके पास ये चीज जो बचेगी वो हो जाएगी पार्शियल यू बाय पार्शियल एक्स। अब ये चीज हमारे पास आ गया रेट ऑफ चेंज ऑफ वॉल्यूम इन एक्स डायरेक्शन पर यूनिट वॉल्यूम। वो हमारे पास आ गया एक्स डायरेक्शन के लिए। ये चीज आपके लिए बहुत इंपॉर्टेंट है। और ये किसके इक्वल है, नॉर्मल वेलोसिटी ग्रेडियंट के इक्वल है इन एक्स डायरेक्शन, नॉर्मल वेलोसिटी ग्रेडियंट। ठीक हो गया, ये एक्स डायरेक्शन को आपने ये चीज। अब इसी तरह अगर मैं यही चीज मैं वाई डायरेक्शन में निकालना चाहता हूँ तो वो किसके इक्वल आएगी, रेट ऑफ चेंज ऑफ वॉल्यूम इन वाई डायरेक्शन। इफ आई वांट टू इन वाई डायरेक्शन, अगर यही वाली चीज हो तो दैट वुड बी इक्वल टू पार्शियल वी बाय पार्शियल वाई। ठीक है। और इसी तरह अगर यही चीज मैंने निकालनी हो जी डायरेक्शन में तो वो मेरे पास आ जाएगी पार्शियल डब्ल्यू बाय पार्शियल जेड। ठीक है, इज इट क्लियर?
सर ये भी सर वाई और जेड डायरेक्शन में भी इनको नॉर्मल वेलोसिटी ग्रेडियंट कहेंगे।
बिल्कुल, ये नॉर्मल वेलोसिटी ग्रेडियंट है क्योंकि बी जो वेलोसिटी है वो वाई डायरेक्शन में होती है, तो वो उसी डायरेक्शन में उसमें चेंज आ रहा है जिस डायरेक्शन के लिए वो वेलोसिटी है। ठीक है, तो ये भी नॉर्मल है, नॉर्मल ग्रेडियंट है। तो
ओके सर,
ठीक है, तो ये वाली जो चीज है जी जी का ये
यू की जगह सिर्फ वी लिख देंगे।
बी नहीं तलहा, इज इट तलहा?
यस सर।
जी तलहा, देखे ना यू की जगह हमने वी लिखा लेकिन जो डायरेक्शन है वो एक्स की जगह हमने वाई की, और फिर यू की जगह जब डब्ल्यू लिखा तो फिर उसकी डायरेक्शन लिखी ना, बी लिखी, एक्स की जगह बी लिखी थी।
ठीक है सर, वो पता लग गया। मैं ये कहता हूं जब हम एक्सेस जो है वो मतलब y के हमेशा जो है वो हम e से डिनोट करेंगे
जी, यानी कि बी को वाई के साथ, डब्ल्यू को वी के साथ। ठीक है ना?
ठीक है सर, थैंक यू।
ओके जी, थैंक यू। तो नाउ इफ यू सी दैट ये ट्रांसलेशन तो काफी सिंपल थी कि उसमें मैंने जैसे बताया था कि यू और वी की जो वैल्यू है वो हर जगह पे वही रहती है, तो वो ट्रांसलेट कर देता है। और जो डिस्टेंस ट्रांसलेशन का निकालना हो कि डिस्प्लेस कितना हुआ है तो यू इंटू डेल्टा टी किया जा सकता है। और उसमें एक चीज लास्ट पॉइंट अगर आप देखें, ऑल पॉइंट्स इन द एलिमेंट हैव द सेम वेलोसिटी। वेलोसिटी ग्रेडियंट विद इन द एलिमेंट आर ऑलवेज जीरो, यानी कि ना ही कोई नॉर्मल वेलोसिटी ग्रेडियंट होगा और ना ही कोई टेंजेंशियल वेलोसिटी ग्रेडियंट होगा, ठीक है। तो ट्रांसलेशन के अंदर जो पहला डिफॉर्मेशन की टाइप है उसके अंदर कोई वेलोसिटी ग्रेडियंट नहीं है। अब आ जाता है दूसरा जो कि अभी हमने देखा है लीनियर डिफॉर्मेशन। लीनियर डिफॉर्मेशन के अंदर जैसे मैंने बताया है कि नॉर्मल वेलोसिटी ग्रेडियंट कॉज डिफॉर्मेशन, ठीक है। और डिफॉर्मेशन या वो स्ट्रेच कर सकता है या वो कंप्रेस हो सकता है, ठीक है। लेकिन उसमें वॉल्यूम चेंज होता है लेकिन शेप चेंज नहीं होती, ठीक है। वॉल्यूम या बड़ा हो सकता है या छोटा हो सकता है लेकिन शेप उसकी वही रहेगी। जैसे यहाँ पे देखें तो ये वाली जो चीज है ये हमने अभी डिस्कस की है कि ये वॉल्यूम कितना चेंज होता है पार्शियल यू बाय पार्शियल एक्स इंटू डेल्टा एक्स इंटू डेल्टा टी, ठीक है। ये हमने अभी व्हाइट बोर्ड के ऊपर ये हमने स्टडी किया था कि अगर यहाँ पे यू वैल्यू हो और यहाँ पे हम टेलर सीरीज से यू प्लस पार्शियल यू बाय पार्शियल एक्स कर सके तो ये हमारे पास इस तरह हम इसको जो चेंज इन वॉल्यूम है, जो चेंज इन वॉल्यूम है वो अगर निकालनी हो तो उसको डेल्टा वाई और डेल्टा बी जो कि फेस है, फेस का एरिया उससे मल्टीप्लाई कर दिया। फिर रेट ऑफ चेंज अगर निकालना हो तो जैसे अभी हमने देखा रेट ऑफ चेंज ऑफ वॉल्यूम पर यूनिट वॉल्यूम दैट वाज इक्वल टू पार्शियल यू बाय पार्शियल एक्स। Similarly, for the rate of change of volume per unit volume in y direction, that would be equal to partial u by partial v by partial y and partial w by partial z. और अगर हमने total rate of change of वॉल्यूम निकालना हो तीनों डायरेक्शन में तो हम उन तीनों को ऐड कर देंगे, जो कि हमने अभी इंडिविजुअल डायरेक्शन में निकाला था उसको हम ऐड कर देंगे। तो वो हमारे पास आ जाएगा पार्शियल u बाय पार्शियल x प्लस पार्शियल v बाय पार्शियल y प्लस पार्शियल w बाय पार्शियल z, और उसको वेक्टर फॉर्म में हम लिख सकते हैं डेल डॉट v, ठीक है।
सर डायरेक्शंस भी लगेंगी ना इसमें आई जे के?
बिल्कुल, डेल डेल फंक्शन अगर आपको याद हो डेल को कैसे लिखते हैं, आपने FM1 में पढ़ा होगा डेल किसके इक्वल था।
सर इसी तरह पार्शियल बाय पार्शियल एक्स आगे कोई भी वैल्यू हो आई हैड प्लस पार्शियल बाय पार्शियल वाई आगे वैल्यू कोई भी हो।
अगर डेल फंक्शन आप लिखना चाहें दैट मींस इक्वल टू पार्शियल बाय पार्शियल एक्स इनटू आई प्लस पार्शियल बाय पार्शियल वाई इनटू ये यूनिट वेक्टर है पार्शियल जे प्लस पार्शियल बाय पार्शियल जेड के, ये होता है ना। उसके बाद आप v को मल्टीप्लाई करेंगे तो v के अंदर u और अब यहाँ पे आ जाएगा और i 1 बन जाएगा, तो आपको पता ही है ना उसका जब आप डॉट प्रोडक्ट करते हैं, ठीक है। तो उसमें उसको आप डेल डॉट v लिख सकते हैं, ठीक है। रेट ऑफ चेंज ऑफ वॉल्यूम, अच्छा जी ये तो हमारे पास हो गया। अब रेट ऑफ चेंज ऑफ वॉल्यूम पर यूनिट वॉल्यूम को हम वॉल्यूमेट्रिक डायलेशन रेट भी कहते हैं। इसका जो नाम है ये जो हम डेल डॉट v को हम वॉल्यूमेट्रिक डायलेशन रेट भी कहते हैं। और अगर हमारे पास इनकम्प्रेसिबल फ्लूइड होगा तो उसमें वॉल्यूमेट्रिक डायलेशन रेट क्या होगा, if the fluid element is incompressible, what would be the volumetric dilation rate for it? जीरो, क्योंकि वो कंप्रेस नहीं हो सकता तो उसका मतलब क्या है कि उसका वॉल्यूम चेंज नहीं हो सकता। जब वो वॉल्यूम चेंज नहीं होगा तो वॉल्यूमेट्रिक डायलेशन रेट फॉर इनकम्प्रेसिबल फ्लूइड इज इक्वल टू जीरो। तो आमतौर पे जो लिक्विड होते हैं उनको हम आमतौर पे लिक्विड को इनकम्प्रेसिबल कहते हैं, और जो गैसेज होती हैं उनका वॉल्यूम हम चेंज कर सकते हैं, ठीक है, क्योंकि उनकी डेंसिटी चेंज कर सकते हैं, ठीक है। तो आई होप कि ये वाला पॉइंट क्लियर होगा आपको। और अब नेसेसरी कंडीशन क्या है लीनियर डिफॉर्मेशन के लिए, नॉर्मल वेलोसिटी ग्रेडियंट, यानी कि इसमें से अगर पार्शियल u बाय पार्शियल x हो, पार्शियल v बाय पार्शियल y हो या फिर पार्शियल w बाय पार्शियल z हो, देन वी कैन हैव द लीनियर डिफॉर्मेशन। नाउ वी मूव ऑन टू द थर्ड टाइप ऑफ डिफॉर्मेशन व्हिच इज रोटेशन। जैसे कि मैंने आपको पहले भी बताया था कि जो रोटेशन होती है वो भी रिजिड बॉडी मोशन होती है, जिसके अंदर वो पूरे का पूरा एलिमेंट इट रोटेट्स ड्यू टू सम टेंजेंशियल वेलोसिटी ग्रेडियंट, ठीक है। हमने शुरू में पढ़े थे ना नॉर्मल वेलोसिटी ग्रेडियंट और टेंजेंशियल वेलोसिटी ग्रेडियंट। तो टेंजेंशियल वेलोसिटी ग्रेडियंट की वजह से रोटेशन होती है, ठीक है। तो अगर हम उसको देखना चाहें स्लाइड के ऊपर, इफ वी कैन डू इट क्विकली, इट इज नॉट वेरी डिफिकल्ट, बट now if when it would be we would have the rotation when we have got tangential velocity gradient। tangential का मतलब ये होता है कि अगर u velocity x में ना चेंज हो रही हो बल्कि y में या फिर z में चेंज हो रही है। यहाँ पे अगर देखें ये जो एलिमेंट है जो कि ओरिजिनल एलिमेंट था जिसके यहाँ पे वर्टिसेस पे जो वेलोसिटी है वो u और v है, तो उसके y डायरेक्शन में अगर अपर फेस पे देखें तो u वेलोसिटी बढ़ गई है, u प्लस पार्शियल u बाय पार्शियल y इनटू डेल्टा y। ये वाली वैल्यू कैसे हमने लिखी है, बाय द फोरियर सीरीज जो कि हमने शुरू में पढ़ी थी। और इसी तरह अगर देखें तो ये लेफ्ट हैंड साइड पे जो वेलोसिटी है v की वो v वेलोसिटी है, तो राइट हैंड साइड फेस पे अगर देखें x डायरेक्शन में तो v की वेलोसिटी चेंज हो गए v प्लस पार्शियल v बाय पार्शियल x इंटू डेल x हो गई, ठीक है। अब अगर हमें देखना हो कि ये रोटेट कितना हुआ है, उसके लिए हमें एंगल डिफाइन करने पड़ते हैं, डेल्टा अल्फा और डेल्टा बीटा। तो अगर सबसे पहले एंगुलर वेलोसिटी अगर हमने निकालनी हो, क्योंकि अगर देखें ना कि जहाँ पे u ज्यादा है अपर फेस पे, तो ये जो एलिमेंट है ये राइट क्लॉकवाइज चेंज करेगा, और अगर यहाँ पे देखें तो राइट फेस पे v की वेलोसिटी ज्यादा है तो ये एंटी क्लॉकवाइज चेंज करेगा। ये वाली जो OA लाइन है वो OA डैश हो जाएगी, और जो OB लाइन है वो OB डैश हो जाएगी, ठीक है। अब अगर हमने एंगुलर वेलोसिटी निकालनी हो OA की, तो हमें पता है कि दैट इज रेट ऑफ चेंज ऑफ दैट एंगल, ठीक है, डेल्टा अल्फा इंटू डिवाइडेड बाय डेल्टा टी, लिमिट गोज टू डेल्टा टी गोज टू 0। ये सिंपल जो स्टैटिक्स और डायनामिक्स में हम ये पढ़ते हैं एंगुलर वेलोसिटी निकालने के बारे में, ठीक है। आई होप दैट दिस पॉइंट इज क्लियर टू एवरीवन। अब डेल्टा अल्फा किसके इक्वल है वो हम रिप्लेस कर देंगे। फॉर द स्मॉलर एंगल हमें पता है कि टेंजेंट ऑफ दैट एंगल इज अप्रोक्सीमेटली इक्वल टू दैट एंगल, और टेंजेंट अगर हम निकालना चाहें तो वो किसके इक्वल होता है फंक्शन, दैट इज परपेंडिकुलर डिवाइडेड बाय बेस। परपेंडिकुलर किसके इक्वल है, पार्शियल u बाय पार्शियल x इनटू डेल्टा x इनटू डेल्टा t, जो कि ये वाला डिस्टेंस है a डैश, ये पार्शियल u बाय पार्शियल v बाय पार्शियल x इनटू डेल्टा t, और डिवाइडेड बाय डेल्टा x जो कि ये बेस है, ठीक है। और इसको अगर हम सिंप्लीफाई करें वी कैन राइट पार्शियल v बाय पार्शियल x इनटू डेल्टा t, और जब हम यहाँ पे w इस रिलेशन में ये वैल्यू पुट करेंगे तो आपके पास जो एंगुलर वेलोसिटी है WOA की वो पार्शियल v बाय पार्शियल x आ जाएगी, ठीक है। एनीथिंग व्हिच इज नॉट क्लियर ऑन दिस स्लाइड? एवरीथिंग इज क्लियर? एनीवन?
यस सर।
ठीक है।
Yes, sir.
ये सिंपल ट्रिग्नोमेट्री
Yes,
है,
sir.
ये इतना मुश्किल नहीं है, क्योंकि फोरियर सीरीज का आपको पता हो, देन यू कैन गेट द वेलोसिटीज at these faces, and then you need to just find the value of WOA, and similarly we can find the value of WOB. So WOB, if we find the value, that is equal to, now these gradients if you see partial v by partial x and partial u by partial y, they are tangential velocity gradients, ठीक है। तो रोटेशन इज ड्यू टू द प्रेजेंस ऑफ टेंजेंशियल वेलोसिटी ग्रेडियंट। जो लीनियर डिफॉर्मेशन थी वो उसके लिए जो नेसेसरी कंडीशन थी वो नॉर्मल वेलोसिटी ग्रेडियंट थे, और रोटेशन और एंगुलर डिफॉर्मेशन के लिए टेंजेंशियल वेलोसिटी ग्रेडियंट, जो कि पार्शियल u बाय पार्शियल x पार्शियल y या फिर पार्शियल u बाय पार्शियल z भी हो सकता है, पार्शियल v बाय पार्शियल x पार्शियल v बाय पार्शियल z, या फिर पार्शियल w बाय पार्शियल x या फिर पार्शियल w बाय पार्शियल y, ठीक है। तो अगर हमने रोटेट ये मेरे लास्ट पॉइंट हम यहाँ तक कवर कर लेते हैं, द रोटेशन ऑफ द एलिमेंट अबाउट द z एक्सिस। अगर हम z एक्सिस का मतलब ये है कि यहाँ पे आउट ऑफ द बोर्ड अगर हमें देखनी हो कि उसकी रोटेशन क्या है, देन वी जस्ट काइंड ऑफ take the average of both now, because one is anti clockwise rotation, one is clockwise। तो अगर हम एंटी क्लॉकवाइज को पॉजिटिव रोटेशन लेके अगर हम इन दोनों को ऐड कर दें तो देन, क्योंकि अगर देखें ना पार्शियल v बाय पार्शियल x इज द काउंटर क्लॉकवाइज रोटेशन, तो उसको हमने पहले लिखा, और जो क्लॉकवाइज रोटेशन है उसको माइनस के साथ, क्योंकि ऐड जब करेंगे तो वो माइनस के साथ होगी, क्योंकि वो क्लॉकवाइज रोटेशन है। तो एवरेज ले लें तो वो हमें पता चल जाएगा कि ये इसकी रोटेशन कितनी है, इसकी एवरेज रोटेशन क्या है एलिमेंट, ठीक है। अच्छा, अब मुझे ये बताएं कि अगर रोटेशन को जीरो करना हो तो हमारे पास पार्शियल v बाय पार्शियल x शुड बी इक्वल टू पार्शियल u बाय पार्शियल y। इसका मतलब ये है कि जितना ये पार्शियल v बाय पार्शियल x इस डायरेक्शन में गया है, इसी तरह इस डायरेक्शन में इसको इधर को काउंटर क्लॉकवाइज जाना पड़ेगा, तब भी ये प्योर रोटेशन होगी, क्योंकि इस सूरत में तो यहाँ पे एंगुलर डिफॉर्मेशन भी हो रही है, शेप भी चेंज हो रही है ना यहाँ पे। तो अगर हम चाहते हैं कि प्योर रोटेशन हो तो ये जो OB वाली लाइन है ये इस साइड पे होनी चाहिए, यानी कि इस साइड पे, ठीक है। लेट मी क्विकली ड्रॉ इट हियर, दैट इज द लास्ट डिस्कशन पॉइंट फॉर टुडे। कहने का मतलब ये कि ये अगर इस डायरेक्शन में काउंटर क्लॉकवाइज है ना, तो फिर ये वाली भी उतना ही ये इतना काउंटर क्लॉकवाइज होनी चाहिए, ठीक है। यानी कि जितना ये डेल्टा अल्फा था उतना ही ये डेल्टा बीटा, और इन दोनों की डायरेक्शन एंटी क्लॉकवाइज होनी चाहिए, देन इट इज काइंड ऑफ प्योर रोटेशन, ठीक है। अगर इन दोनों की वैल्यू डिफरेंट होगी देन देयर वुड बी सम काइंड ऑफ चेंज इन शेप व्हिच इज एंगुलर डिफॉर्मेशन, ठीक है। तो आई होप दैट दिस पॉइंट इज क्लियर। इसी तरह ये हमने z डायरेक्शन z के लिए निकाली थी, ठीक है, अराउंड अबाउट द z एक्सिस। इसी तरह y के लिए भी हम निकाल सकते हैं और x के लिए भी निकाल सकते हैं। अब आप देखें तो हमारे पास डब्ल्यू जेड का रिलेशन भी है, डब्ल्यू वाई का भी है और डब्ल्यू एक्स का भी है। इनको अगर हमने वेक्टर फील्ड में लिखना हो, लेट मी जस्ट कंप्लीट इट क्विकली एंड देन वी कैन कॉल इट अ डे। हम इस जो वेक्टर फील्ड है इसको हम इस तरह लिख सकते हैं, डब्ल्यू इज इक्वल टू डब्ल्यू एक्स आई प्लस डब्ल्यू वाई जे प्लस डब्ल्यू wzk, and then we can just write it in terms of wz k। इसको अगर याद रखना हो तो वो बहुत सिंपल है कि दिस इज हाफ कर्ल ऑफ वेलोसिटी फील्ड, ठीक है। अब कर्ल ऑफ वेलोसिटी फील्ड निकालने के लिए तो एक मैट्रिक्स है, अगर उसको आप याद कर लें, याद भी नहीं, आई जे के partial by partial x, partial by partial y, partial by partial z, and that here u v w, okay, and this is half, so this is the rotation, ठीक है। तो if I expand it, यहाँ पे क्या आ जाएगा, हाफ इंटू partial w by partial if I want to write partial w by partial y minus partial b by partial z, इसके साथ i आ जाएगा, प्लस हाफ इंटू पार्शियल, यहाँ पे अब क्या हो जाएगा, पार्शियल u बाई पार्शियल z माइनस पार्शियल w बाई पार्शियल x, j हो जाएगा, एंड देन द थर्ड कंपोनेंट वुड बी प्लस हाफ इंटू partial b by partial x minus partial u by partial y. Okay. So now what is this? This is wx, this is wy, and this is wz. Okay. So if you remember this, that omega is, or we call it rotation omega, that is half curl of velocity field. कर्ल कैसे निकालते हैं वो, उसके लिए ये मेथड है आई जे के। So I hope that today's lecture was understandable to certain extent.